Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is for students who are in differential equations and who have already gone through first order differential equations. So you know about separation of variables and linear first order ODEs and exact equations, all that stuff. The basic analytical solution methods. And when I say analytical, I mean solution methods that you can do by hand. In this video, we're going to focus or start our focus on numerical techniques for finding solutions or approximating solutions to differential equations. There actually are three techniques that we're going to use to numerically approximate solutions to differential equations. Now, before we go too far, I want to mention what are numerical methods in general. Like, what do we need them for? Why do they exist? Did we learn about them before? That type of thing. And the reality is we have. So we're going to focus on the what. If you're in differential equations, you've already gone through Calc 2. And in Calc 2, you learned numerical integration techniques that had names like the left endpoint method, the right endpoint method, the midpoint method, the trapezoid method or trapezoidal rule, and then the ever elusive Simpson's rule. Now, to be honest with you, you actually learned at least the first two methods in Calc 1, and then you learn the rest in Calc 2. Sometimes you learn midpoint method in Calc 1 as well. So it just depends on who your instructor was and if they covered that material. I generally like to cover those first three methods, the left endpoint method, right endpoint method, and a little bit of the midpoint method in Calc 1. And then you reserve the other two methods for kind of a higher level analysis in Calc 2. And in Calc 2, what we end up doing is we go through the midpoint. Like I said, in general, I cover that in Calc 1, but again, you kind of hit upon it in Calc 2. So the midpoint method, trapezoidal rule, and Simpson's rule, and you use those to estimate the value of a definite integral. And this is done because you just cannot analytically, in other words, by hand, find the antiderivative for a given function. Well, that's kind of the same thing we're going to be doing here with differential equations. We're going to find a numerical method, or we're going to develop numerical methods that allow us to approximate the solution values to our differential equations that we've been handed if we cannot find analytically a functional solution. And that is often the case, to be honest with you. It's very difficult to find the actual solution analytically to a given differential equation, so we have to resort to numerics. The methods that we're going to employ here are Euler's method, and then another method called improved Euler's method, which is sometimes called the modified Euler's method. And then finally, we'll round it out with a very complex method, actually the beginning of a family of complex methods called the Runge-Kutta method. And I'm probably mispronouncing that. Even though I use it, I still mispronounce it. Over all these years, I still say Runge-Kutta. Sometimes I'll say Runge-Kutta, but that's actually not true. I know that it's not Runge-Kutta, but I think it's Runge-Kutta. Anyway, most people also know this as the RK4 method. And that's because there are other versions of the Runge-Kutta method that involve, well, we'll just say involve more operations. Now, we've already discussed why we need the numerical methods for solving differential equations, so I don't really need to say very much there. Other than that, I want to be very clear that when you are finding solutions to differential equations using these methods, these and many more actually, you're only actually approximating values to the solution. You're not actually getting a function in the end. So when you use these methods, it's not that it's going to pop out some, oh, y of x is equal to sine of x times y or something like that. It is just going to give you numerical approximations to your solution curve that you're aiming for given an IVP near to your initial condition. In fact, I should mention that here. So again, we're asked to solve an IVP, but there's just no way to actually find the solution of that initial value problem by hand. So what we do instead is we approximate the solutions near to the initial condition. Now, how do we go about doing that? Well, to investigate that question, we're going to have to recall some stuff from our Calc 1 course. Or yeah, I guess it would be our Calc 1 course. So we'll now engage into a quick review of some Calc 1 topics that are going to be necessary for our success in finding or approximating solutions to differential equations using numerical techniques. The first thing we're going to need from Calc 1 is to recall that we actually, when we introduced the idea of an integral, partitioned an interval into a bunch of little sub-intervals. So we took some interval from, let's say from A to B, and we diced it into n sub-intervals. Also note, our sub-intervals were equally spaced. That is, each of these widths were all just delta x. Now, once we did that, it was kind of an interesting little side note here that we wanted to make sure that you knew, hey, this first edge, the leftmost edge there that we called A, because we were back then integrating from A to B. Now we're just counting sub-intervals starting at A and ending at B. But we called that first left edge x sub 0. And the rightmost edge of this interval we called x sub n. So we have a bunch of sub-intervals that you can see right there. Again, x sub 0 is A and x sub n is B. And you could easily, from Calc 1, have computed delta x by just saying, well, that delta x is just taking that full length interval from B to A and dividing it into n sub-partitions, or n partitions is what we'd call it. And we, again, define that to be delta x. However, here, we're going to not use delta x, we're going to use lowercase h. It just is a convention, so I hope you don't mind. At this point, I'm going to say, let's replace all those delta x's with h's. And finally, another thing that we did, and it was bothering me that that x sub n minus 3 was not labeled, so I went ahead and labeled it. But another thing that we did was we went ahead and created a formula to represent the ith step within this partition. That is, we wanted to know a formula for x sub I. Well, to get to x sub I on that interval, you would start at A and you would go by steps of size, in this case, h. So I could take I steps of width h starting at the point A, or the x value of A. And of course, A here is actually x sub 0. All right, that quick review of partitioning an interval into n equally spaced sub-intervals is the first part of getting used to numerical techniques for finding or approximating solutions to differential equations, believe it or not. The formula we'll be adhering to quite a bit here, or the formulas we'll be adhering to quite a bit, are this formula right here, h is equal to b minus a over n, and the second formula, which is x sub I is equal to x naught plus hi. Now, to be honest with you, you don't even actually deal with that second formula very much, because what you're going to do with numerical techniques for solving differential equations is, in the long run, you're going to code them into some type of program, either using some type of scripting, or you might use an actual coding language, or you might just use Excel or Google Sheets. But in the long run, you're not going to store all of these x sub I values. You're just going to get to the next x sub I value by starting where you left off and adding h. And then you get to the next one after you're done working on that by adding h, and so on and so forth. The other piece that you need to know as a review from your Calc 1 course is the concept of linearization. And this concept often is taught probably about 2/3 of the way through a course in differential calculus. And the idea is to approximate the values of a curve f that are locally near to some really nice convenient point A. And when I say A, I really mean near the point A comma f of A, to be exact here. The idea is to use a tangent line to approximate the values of this white function f here near to A. So you don't have to actually use the function f. You can use the values of the tangent line for x values near to A. So we can see that sort of looks like the tangent line that goes through A comma f of A on the curve f of x. And you learn from Calc 1 that instead of evaluating f at, well, let's just say at some value, let's say a plus h. If the function f was just too difficult to compute at f of a plus h, well, one thing I do know, lines are very easy to work with at any value. So if I want to evaluate, or estimate I should say, the value of that function f at a plus h, all I need to do is plug a plus h into our linearization of our function f. It was linearized, by the way, at the point a comma f of a. And that point we'll call for now a plus h comma L of a plus h, L being the equation of the line. And you're still evaluating at a plus h because, well, that's the x value you want to evaluate at. So reminding ourselves of the concept, not too hard. And in fact, reminding ourselves of the actual formula is not difficult either, as long as you remember the picture. The picture is very powerful. Think about the equation of a line. You pretty much only need two things to find the equation of a line: slope and a point. And that calls into play this idea of the slope-intercept form. However, we know there's also two forms for the equation of a line. There's a slope-intercept form, but there's also a point-slope form, and I would much prefer the point-slope form, where x sub 1, y sub 1 are points that are on the line. Well, if you take a look at the green line, the tangent line up there, the point that's definitely on it is a comma f of a. So I'll insert that in here. And the slope of that tangent line, or that green line, I should say, is the value of the derivative of f at a itself. And I should use implication signs here, because that point slope form implies L of x minus f of a is equal to m times the quantity x minus a, which implies L of x minus f of a is equal to f prime at a times x minus a. And then finally, that will imply that our equation for our linearization function is just f at a plus f prime at a times the quantity x minus a. Now, this idea of linearization is going to be important as we step into numerical methods for solving differential equations. Very, very important, in fact. So all I wanted to do in this video is really cover what a numerical method is for solving differential equations, and to review this idea of partitioning that we're going to be using, and the idea of linearization at a point, which we will be using. In the next video, we'll actually start into Euler's method, his original method, and then another video we'll do improved Euler's, and then finally we'll have a video just for the Runge-Kutta method. I hope to see you there.